Welcome! In this Class 12 chemistry lesson, we will explain the hydrogen spectrum, including the spectral series, the key formulas, and a couple of worked numericals. Then, as a quick connected concept, we will review polar covalent bonds, partial charges, and dipole moments. Let us begin with the Bohr picture of hydrogen. The electron has allowed energy levels labeled by n equals 1, 2, 3, and so on. When an electron drops from a higher level to a lower level, a photon is emitted. The color or wavelength of that photon gives a spectral line. Here is a simple energy level ladder for hydrogen. We will show a few example downward transitions that produce light. Spectral lines of hydrogen group into series, each characterized by a common lower level. The Lyman series has final level n equals 1 and lies in the ultraviolet. The Balmer series has final level n equals 2 and includes the visible lines. The Paschen series has final level n equals 3 and lies in the infrared. We also have Brackett, Pfund, and more at even longer wavelengths. Now for the key formulas. The Bohr energy of level n is E sub n equals negative 13.6 electron volts divided by n squared. When an electron drops from n initial to n final, the photon energy equals hc over lambda equals E initial minus E final. This leads to the Rydberg formula for hydrogen. 1 over lambda equals R sub h times the quantity 1 over n final squared minus 1 over n initial squared. Here are the constants we will use. Rydberg constant 1.097 times 10 to the 7 per meter, Planck's constant 6.626 times 10 to the minus 34 joule second, and the speed of light 3.00 times 10 to the 8 meters per second. Numerical 1. Find the wavelength of the Balmer transition from n equals 3 to n equals 2. We write 1 over lambda equals R sub h times open bracket 1 over 2 squared minus 1 over 3 squared close bracket. That is our sub h times, open bracket, 1/4 minus 1/9 close bracket equals our sub h times 5 over 36. Putting our sub h equals 1.097 times 10 to the 7 per meter, we get 1 over lambda approximately 1.524 times 10 to the 6 per meter. Therefore, lambda is about 6.56 times 10 to the minus 7 meters, which is 656 nanometers, the well-known H-alpha red line. Numerical 2, Lyman transition from n equals 2 to n equals 1. Find the wavelength and photon energy. We write 1 over lambda equals our sub h times, open bracket, 1 minus 1/4 close bracket equals 3, our sub h over 4. Numerically, 1 over lambda equals 0.75 times 1.097 times 10 to the 7 per meter equals 8.2275 times 10 to the 6 per meter. So lambda is about 1.216 times 10 to the minus 7 meters, 121.6 nanometers, which is ultraviolet. Photon energy is hc over lambda. Substituting, we get about 1.636 times 10 to the minus 18 joules, which is around 10.2 electron volts. Before we close, a quick connected concept in chemical bonding that you will often see in Class 12, the polar covalent bond. This helps explain why molecules like water interact with light and with each other. A polar covalent bond forms when two atoms share electrons unequally because of different electronegativities. If the electronegativity difference delta En is between 0 and 0.4, the bond is essentially nonpolar covalent. Between 0.4 and 1.7, it is polar covalent. Greater than 1.7, it is usually ionic. The more electronegative atom pulls electron density and becomes delta minus. The less electronegative atom becomes delta plus. We describe the bond polarity by a dipole moment mu equals Q times R, often measured in debye, where 1 debye equals 3.335 times 10 to the minus 30 coulometer. Example, hydrogen chloride. Chlorine has electronegativity about 3.0, hydrogen about 2.1, so delta En equals 0.9, which is polar covalent. Hydrogen bears delta plus, chlorine bears delta minus, and the bond dipole points from hydrogen toward chlorine. More examples. In water, the oxygen is more electronegative. Each O-H bond is polar, and because of the bent shape, the molecular dipole is non-zero. In hydrogen fluoride, The bond is strongly polar with hydrogen delta plus and fluorine delta minus. In carbon tetrachloride, each carbon-chlorine bond is polar, but the tetrahedral symmetry makes the overall molecule nonpolar since bond dipoles cancel. Summary: in the hydrogen spectrum, spectral lines arise from electron transitions between quantized levels and are grouped into series like Lyman, Balmer, and Paschen, described by the Rydberg formula. In bonding, unequal sharing of electrons produces polar covalent bonds with partial charges and a dipole moment. Keep practicing numericals to master both topics.